Corporate finance practice problem using Onenote. Standard deviation, variance, and coefficient of variation calculations. Get ready, it's time to take your chance with corporate finance. Here we are in Onenote. If you have access to Onenote, would like to follow along, you're not required to, but if would like to, we're in the icon left-hand side. We're going to be in the Practice Problems tab, then in the 1300 Standard Deviation, Variance, and Coefficient of Variation tab. Also note, when using Onenote, look at the Immersive Reader tool. Our presentations up top will be down in the text area below. Text area with the same name, same number, and transcripts. Transcripts that can be translated into multiple different languages and either listened to or read in them. Closing the icon, we have our information up top, going through some calculations on down below. This presentation will be on statistical type of tools and concepts, a more mathematical type of presentation that we'll then use. We'll take these tools and then use them in projections and whatnot in future presentations. So this is focused more on the math to remind us about math related to basically a series of numbers. And being math, there's a lot of great information on mathematical concepts such as these: standard deviation, variance, and coefficient of variation. So you can search them on Google or any kind of whatever browser you want, or YouTube, and you could probably find a lot of good information on it. We're basically looking at a data set, a set of numbers, and trying to get an idea about that set of numbers. The set of numbers possibly being a full population, the numbers representing a population of something, or they could be representing a sample of something. We're typically going to use full population type of calculations here. And note, when you're thinking about statistics, then a lot of people are really skeptical about statistics because they hear the idea of basically people can lie with statistics. And that's true, people can lie with statistics, but people can lie with anything, right? What people usually do when they lie with statistics, just like when they lie with anything, is they pull one piece of truth and then they build a bunch of lies around that one piece of truth that's basically holding up the whole thing of lies, right? And you could do that with one piece of truth in a verbal argument and whatnot as well. And statistics is vulnerable to that as well. But note, if you're doing statistics honestly, then what you're really trying to do is not get one piece of data. You want to analyze the population size with multiple pieces of data so that you can get a better idea of what the actual data set is saying. And that's kind of the idea of looking at statistics oftentimes when you're trying to figure out what the data set actually means. You'd like to take a look at it at different views, break it out in different ways, different perspectives at the data so you can see what it is representing, in reality. So some of the concepts we'll take a look at is the population mean, the average of the population data points. So the mean, remember, is basically the average where you're going to sum up the population data points and then divide them by the population, which are the number of items that you're summing up. So that's going to be could be called the mean, or it could be called the average. And don't get that mixed up with the median, which is kind of like that center number. So that's usually kind of one of our starting calculations when we're looking at a series of numbers. Then we want to take a look at the variance, which is the dispersion of a set of data points around the mean. So that looks like a formula such as this. Population variance is going to be each data point minus the mean, and then we're going to square it divided by the population size again. The variance is going to be a concept that'll give us then an idea of how much spread there is around the mean. So if you think about the mean, the average, then the next thing we want to look at is how clustered are the sets of data points around the average. So for example, obviously, if you take each data point here minus the mean, the closer the data point is to the mean, then the smaller the number you're going to have here, and then we're going to square it. So that'll be the concept of this, and then we'll move from there with the population variance. But that's the general concept that we want, right? We'll take the average, which is kind of like the middle. It's not the median, but it's the average. It's the mean. And then we want to think about the variance being how dispersed are the data around that center point, which we have as the average. So to look at this, let's take a set of data points. So we'll just count from 1 to 5. Let's start out counting from 1 to 5. And do some of our analysis just based on that series of numbers. So we have this series of numbers. It could represent some population of something. Our typical type of calculation with it would be possibly to total it up, adds up to 15. If we divide that by the population size, which is 1, 2, 3, 4, 5, there's 5 of them, of course, and that would give us the mean or average. So the 15 divided by 5 would be the 3. That would probably be our starting point when we're trying to analyze a set of numbers. Now, if we want to think about the population variance, then we could do something like this. We can use this calculation here, taking each of the numbers in the set minus the mean squared over the population, which if we did that mathematically would look like this. 1 minus 3, the mean, so that's the 1 minus the 3 down here, plus 2 minus 3, 2 minus 3 squared, plus 3 minus 3, 3 minus the mean, 3 squared, plus 4 minus 3 squared, 4 minus the 3 squared, and then 5 minus the 3 squared, divided by the population, which is 5. 1, 2, 3, 4, 5 in the population, and that would give us the variance. If you do this like in an Excel type of calculation, it would typically look something like this. We could set up our numbers here. We can then take the mean, which is 3. So we're taking each number in our data set. Then we're taking 3, the mean, and we're going to compare them out. This is this part of it, of course. 1 minus 3, 2 minus 3, 3 minus 3. So if we take the difference, then we've basically done the whole numerator without squaring it. So now we're going to square each one of them, and we've got these differences that we're going to square. Also note, when we have these differences here, some of them are negative and some of them are positive. And because these are distances from the mean, which is kind of like you're imagining the center point of this whole thing, they need to be positive. So one way to get them to be positive is to square them. So squaring them will both make them positive and amplify the results. So if we square them, if you pull out a trusty calculator, remember if you do this in a book problem, you need a calculator that can handle the squaring. This one has a square button here, so you could say the 2 squared. So that's going to be then the 4 here. But I think if you have anything other than squaring, you might have to use a different calculator, which in the Windows calculator might be a scientific one, which you can get to by going to this little drop-down scientific calculator. And then you could take then the same 2, and I'm going to say negative 2. Let's take the 2 and then negative. And then you can go to the x to the y, and then we're going to take it to 2. And then there it goes. And it turns out to be, of course, the positive 4. That's going to be one of the functions of squaring it. So I'm going to go through here. If you did the same thing here, squaring the 1, you're going to get 1, negative 1, positive 1, 0 is 0, and then positive 1 is 1 if squared, and then positive 2 is 2 if squared. So that's basically our numerator up top. Once we have that, then we could take a look at we could sum them up, and that's our numerator. Adding this up, the 4 plus the 1 plus the 1 plus the 4, there's the 10. Then we divide by n, which is 5, the population, 1, 2, 3, 4, 5 of them in the data set. So the 10 divided by 5 is going to give us 2, that being the population variance, Now the population variance is squared, right? We still have this kind of squared component in it. So it's often useful then to take that population variance and take the square root of it. So if we take that population variance of 2 and then square root, we get the 1.41421 about. So that's going to be then the standard deviation. So that's what's going to be called the standard deviation. And then if we take the mean and we take that number, the 1.4 so on, divided by the average or mean, divided by 3, we're going to get then the 0.471 and so on, and about 0.47, which is going to be the coefficient of variation. This might be represented in a percent or in a decimal. So this number is going to be useful for us typically when we're measuring two different data sets, and it'll become more clear as we go down and we see those two different data sets. So again, normally you got the mean, and then you're basically calculating the population variance to get an idea of the range around the mean. Taking the standard deviation then removes kind of the squared component that you had up top, the squared component kind of amplifying the number, as well as removing the negative values, which gives us then the standard deviation. And then oftentimes we want to basically take the coefficient of variation, because that'll help us to compare two different basic data sets of numbers, and that'll become more apparent in the next presentation. Also note that you could, well, not in the next presentation, our next example problem down here where we'll do a comparison. So note you could do these in Excel as well, and we do this in Excel so you can see it there. So oftentimes when you see this in an Excel worksheet, you'll see it just mapped out and using the Excel calculations to calculate these. Note that it's often useful to actually map out the numbers this way, because mapping this out in Excel actually gives you an idea of what the numbers look like. You can see like this difference column having the negative and positive numbers. That in and of itself gives you a pictorial view of the numbers, of what's actually happening with the numbers. So it actually gives you more information to map this thing out in this format and see the numbers pictorially in that way, and that can help you to visualize what the data set actually means. So if we go down below, we could take the mean or average, and in Excel, that would be the formula of equals the average. And then you take the sum of the data, which would be these 5 numbers, sum of the 5 numbers, and that would give us 3. The average, of course, being adding up those 5 numbers, dividing by the number of units, which was 5. And then we can take the standard deviation. That's going to be the STDEV dot P. Now there's a dot P formula and there's a dot S formula, which can be slightly different whether you're taking the population or the sample. We're going to be working with population calculations here. If you're interested in the difference between the population and standard and sample, then there's a lot of information about that if you research it on your favorite browser search or a YouTube search or something like that. And then we're going to take the variance. So you could do that with a formula, which would be equal VAR dot P. Once again, there's a difference between P standing for population and S, which would stand for the sample. And then take the range of the data. Notice the range of the data is all the same here, which is our data set 1 through 5. And that gave us our 2, of course. And then we got the coefficient of variation, which would be the same calculation, the same format that we did up top, that taking the standard deviation over the mean, standard deviation divided by the mean. So you could basically represent your data pretty quickly with the use of Excel formulas if you had access to Excel. But remember, of course, we want to understand what is actually happening so that these numbers say something to us, so they actually mean something for us so we can analyze the data. Now, if we have 2 data sets, let's take these 2 data sets. First one, 1, 2, 3, 3, 5, 6, 7, 8, 9, 11. So it's not just 1 through 11. We got a couple repeating 3s here, and it skips 10 to 11. And then the second data set is 20, 40, 60, 60, 100, 120, 140, 160, 180, and 220. And so what we want to do is compare these 2 data sets with our analysis here. Now, there should be some similarities with these 2 data sets. So, and we would like our analysis to kind of give us a pictorial representation of them to kind of see what those similarities are. And you might see it here. The pattern is basically this data set 2 is just 20, or the data set 1 times 20, right? 1 times 20 is 20, 2 times 20 is 40, 3 times 20 is 60, 3 times 20 is 60, and so on. So notice these data sets, if they were represented in dollars, for example, are representing different dollar amounts, but the variance around basically the mean has something in common. They're exactly the same in the disbursement in a sense, and we'd like to capture that in our analysis when we're thinking about our data analysis. So let's break down our data analysis down here, and we'll do the same kind of thing. And so note we're taking basically this formula now, the population, hold on a second, the population variance. So we'll take our data then, let's pick up our data. This is the first series of numbers here. And then we'll pick up the mean, which I'm going to just simply calculate the mean for us. Now the mean calculation, if we were to do this with a trusty calculator, take me a little second here. It's going to be 1 plus 2 plus 3 plus 3 plus 5 plus 6 plus 7 plus 8 plus 9 plus 1, and divide that by, I think there's 10, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, divided by 10. Mean or average is the 5.5. So we're going to take our data set and subtract minus the mean or average 5.5. So 1 minus 5.5 is 4.5. 2 minus 5.5 is the negative 3.5. 3 minus 5.5 is a negative 2.5. 5.5 3 minus 5.5, negative 2.5, 5 minus 5.5, negative 0.5, 6 minus 5.5, 0.5, 7 minus 5.5, 1.5, 8 minus 5.5, 2.5, and 9 minus 5.5, 3.5, 11 minus 5.5, 5.5. So now we took our differences here, and now we'll square them. So that's basically our numerator. We're going to square them now. So if I take the 4.5 and square it, I'll just do one of them in the trusty calculator here. So if we do the trusty calculator and just take the 4.5 and squared, we get the 20.25. 20.25 gets rid of the negative and amplifies it. So the 3.5 squared is 12.25, 2.5 squared is 6.25, 2.5 squared is a 2.25, the 0.5 squared is the 0.25. Obviously, these ones closer to the mean that you can see here, and in squaring them, then we'll square them, removing the negative sign and amplifying them. So we got the 0.5 is the 0.25, the 1.5, the 2.25, the 2.5, the 6.25, and so on. So then if we add these up, the total on the squared items, if I add up this column, is going to be the 9650. 9650 population size, just counting them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of them. So the 96.5 divided by the 10 is the population variance, the 9.65. But note, again, this variance has kind of like those squared numbers in them. So although this gives us a variance, if we're talking dollars here, we're talking about like squared dollars. So we want to now kind of remove the squared component from the population variance, would give us the standard deviation, the 3.11, which if they were in dollars would be like dollar units. But then we might want to divide by the mean, the 5.5. So 3.11 divided by the 5.5 gives us the coefficient of variation. This number not too useful for us unless we're comparing it to another set of data, because it gives us basically an idea of one set versus the other. So let's take a look at the second set here, second set of numbers, the 20, the 40, and so on, same set as here. The mean then, if we calculate the mean, let's do that. That'll be fun. Let's just do it. 20 plus 40 plus 60 plus 60 plus 100 plus 120 plus 140 plus 160 plus 180 plus 220 divided by the number of units, 10 of them, if I counted them out, divided by 10. So divided by 10 is going to give us the 110. So that's going to be the average all the way down, 110. And then we'll take the difference between these. And notice as we take the difference, we'll start to see some similarity between these two numbers because of the similarity and disbursement, right? So we got the 20 minus the 110 is 90. Negative 90, the 40 minus the 110 is negative 70, 60 minus 110 is negative 50, 60 minus 110 is negative 50. You can see kind of a parallel trend here that's happening. And then 100 minus 110 is 10, the 120 minus 110 is 10. So you can see a similar trend happening as we go through these differences. The 140 minus the 110 is 30, the 160 minus 110 is 50, the 180 minus 110 is 70. And then the 120 minus 110 is 110. Now, if we square these, then we're going to take them all and square them. I'll just do one of them. So if we took that 90, for example, 90 or negative, and it would be a negative 90, and squared, it's going to be the 18100. So we got the 8100. 70 squared, 4900. 50 squared, 2500. 50 squared, negative 50 squared, 2500. Negative 10 squared, 100, and so on. So then we're going to go on down and say the totaling up the squared numbers, in this case gives us the 38,600. If we take the population size, which is just 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of them, divided by 10, we're going to get the population variance, the 3860. But again, these are in like squared units. So if these were dollars, it'd be like squared dollars. So if we take that and take the square root of it, we get then the standard deviation. So we're taking the square root, which would be the 3860, and we're square root, which would give us the 6212 about, or 6213. And so that's going to be in dollar, but notice I can't really compare that to what happened with this series of data. So that's often useful to us, but what we're going to be looking for oftentimes with our analysis is to divide that by the mean and give us the coefficient of variation. And so now this number is relevant to us because when I compare the two items, that's given us a relevant comparison. So we have different amounts, which you can imagine being different dollar amounts. But when I compare them out, this coefficient of variation gives us a number that gives a better kind of variation of those different dollar amounts around, basically the mean, which can be a useful comparison to us. This is telling us that these two data sets have a similarity, which we can't really get from the other calculations, the population variance or the standard deviation, as easily. Now, of course, you can calculate these with the calculations in Excel. We could take the mean of the first data set, simply averaging up the data set equals average, and then taking the data set, which would be the range of data 1 through 11. We can then take the standard deviation, which would be the STDEV.P if it's the population size of, once again, that data set, giving us that 3.11, matching the 3.11 up top. And then we could take the variance, which would be the VAR.P for the population of, once again, that data set, giving us the 9.65, and then the coefficient of variation being calculated the same way as up top, standard deviation divided by the mean. If we did that for data set 2, same kind of idea. We can do this with Excel with the second data set over here and get a quick calculation. But remember and note that when you actually list out the data set, we can start to see pictorially, actually, the similarities with the data set. So it's actually useful to map them out in sometimes this way, because you can glean information. And that's what you're trying to do a lot of times with a lot of different statistical situation. You're trying to picture the data, these numbers that represent real things, right? And try to see it from different angles. And mapping out the data, if it's not too large and you have the capacity to do so in that way, could actually be useful.